So in this second part of the topic, we're going to actually start using the definitions that we've established in the first part, and we're going to do so in an area called number theory. Now, number theory is the study of structure and patterns in the natural numbers and the integers, and it's a huge topic. Number theorists I like to see as kind of like the F1 drivers of mathematics. They're the trendsetters, I suppose. They're the ones that are pushing mathematics forwards so that other mathematicians can use those tools for problems closer to the real world. We're going to obviously look at one very specific part of number theory, and it's on proofs involving divisibility of numbers. Before we do that, we better talk about what we mean by divisibility. So let's define that now. Divisibility means if I've got two integers a and b, and I say that b is divisible by a, then there must exist some other integer m, so that b equals am. Now that sounds a little abstract, but let's put it into the context of some actual numbers, and you'll see it makes perfect sense. So if I say 20 is divisible by 4, that's true because 20 equals 4 by 5. It just means that I can write b as some multiple of a. Okay, and we're going to sometimes use a symbol to denote divisibility, and it's basically that vertical line there. And I would write 4 divides 20, or 20 is divisible by 4 in this way here. So let's go through some proofs now involving divisibility. So we're going to start with two integers a and b, and we're going to say that they're both divisible by 3, and then we're going to prove some results from that. Okay, so we're going to prove firstly that a plus b is also divisible by 3. It's a fairly simple, straightforward proof. So we'll start by establishing what we know. We're told that a and b are both divisible by 3, and from our definition of divisibility, that means that there exists an m and n in the integers, so that a is equal to 3m and b is equal to 3n. So a is some multiple of 3 and b is a different multiple of 3. They could possibly be the same, but we like to keep it nice and generic here so that we don't lose generality, because they may not be the same multiple of 3. So now we can just add those two things together. What is a plus b? Well, it's 3m plus 3n. There's a common factor of 3, and therefore I can rewrite that bracketed term m plus n as just another integer p, since m and n are both integers. Adding integers is still an integer. So we're basically proving the result at that point, that a plus b is some multiple of 3. Saying that another way, a plus b is divisible by 3. Now let's prove a more general result. Here we're saying that we want to prove that ax plus by is divisible by 3 for all integers x and y. So x and y can be whatever integers we want. We don't care. We're saying that if a and b are divisible by 3, then ax plus by is also going to be divisible by 3. And this is a critically important result in number theory, but the proof's fairly straightforward. Again, we're going to start with that idea that if a and b are both divisible by 3, then we can say that a is a multiple of 3 and b is another multiple of 3. Not necessarily the same, that's why we're using different letters. Then we can generalize now to say, well, what is ax plus by? Well, that's just 3mx plus 3my. Again, pull out the common factor of 3 and write that in simpler terms as 3p. So p is just the integer mx plus my. Therefore, we've said that ax plus by is a multiple of 3, and therefore it's divisible by 3. Here's a more complicated example. And in fact, here we're going to prove an equivalence. We're going to prove that if 7 divides n, then that's equivalent to 7 dividing x minus 2y. And to do that, remember what equivalence means. It means there's an implication running in both directions. So we've got to prove both a statement and a converse here. Let's start with the original statement. So we're going to prove first that if 7 divides n, then 7 also divides x minus 2y. So if 7 divides n, so here we're told 7 divides n running this way, then that means that 10x plus y is some multiple of 7. And rearranging that, then that means that y is equal to 7m minus 10x. Okay, and we can double that result, and you'll see why in a second. We can double that result and get that 2y is 14m minus 20x. And the reason we doubled it is because we need this x minus 2y term here. We need to double y to work with this result. Okay, so we can say from the result that we just got that 2y is 14m minus 20x, we do x take away that, x take away 2y, then we get x take away 14m plus 20x. This minus 20x term here has a double negative, so it becomes a positive. Okay, so that tells us then that x minus 2y must be 21x minus 14m, which has a common factor of 7, which means that, as we've said, x minus 2y must be a multiple of 7. So we've proven the result. If 7 divides n, then 7 divides x minus 2y. We now need to prove the converse. We need to prove the other direction. So here we know that 7 divides x minus 2y, and we want to use that to establish that 7 divides n. Okay, and it's important when we're proving an equivalence that we prove both directions, because we may find that one direction works and the other one doesn't. So it's not always that both work. We need to prove in both directions. Here both do work. We're going to see that this proof works as well, but it doesn't always happen. So here we're told that 7 divides x minus 2y. We know that's true, so let's state that another way, that x minus 2y is equal to 7q. I've used a different letter here from p before, just to keep things different. Okay, so we can then say that x minus 2y is equal to 7q. That's the same thing as saying that 10x is equal to 70q plus 20y. Just check that you can see that they are in fact the same thing. And therefore we can say, given that we know n is equal to 10x plus y, that n is equal to 70q plus 20y plus y, plus that extra y in the end there. We've just replaced the 10x here into the 10x up here, and we can write n in that way, which means that we can write n as 70q plus 21y, and again there's a common factor of 7 there, therefore we've proven the result, that if 7 divides x minus 2y, then 7 divides n. So we've now proven the result both directions. It doesn't matter which way we write it, they're equivalent. So if 7 divides m, we now know 7 divides x minus 2y. Okay, let's solve a real problem now. We want to determine whether 3,871 is divisible by 7. Obviously we could use a calculator to do that, but we want to establish whether this result is true using what we've just done, using some number theory. Okay, so we can use the previous theorem, and it is a theorem now, we've proven it. What we need to do then is write 3,871 in the right way. We need to write it as 10x plus y. So we can easily do that. 3,871's the same thing as 387 times 10 plus 1. So here's our x and here's our y. So what our theorem tells us is that if 7 divides 387 minus 2 times 1, x minus 2y from the previous theorem, if 7 divides x minus 2y, then it divides n, and n was 3,871. So if we can establish that 7 divides 385, then we'll know that it divides 3,871. Okay, now the power comes in. We can use this as if we're starting all over again. We want to establish whether 7 divides 385, so let's use the theorem again. I can write 385 as 38 times 10 plus 5. So this time our x is going to be 38 and our y is going to be 5. So again, we can say if 7 divides 38 minus 2 times 5, that's our x minus 2y, and that's equal to 28, then 7 divides 385. Well, here we go. We've solved the problem now, because 28 is 7 times 4. We know that 28 is a multiple of 7, so it does in fact divide 28, which from the theorem implies that it does divide 385, which again implies that it does divide 3,871. So we've established, using this theorem recursively, that 3,871 is divisible by 7. And we didn't need to use a calculator, and we could do it quite quickly. Okay, so there's a few examples of how we can use divisibility to solve problems. And in the next lesson, we're going to work on the whiteboards, and we're going to solve a whole heap of problems, prove a whole heap of problems using some divisibility.